So here's the good news. We can get f of 0 pretty easily by substituting 0 in for x into our function f. Nice. Okay. We run into problems though when we want f prime and f double prime and f triple prime and the fourth derivative and the fifth derivative and the sixth derivative, because we don't have any of those. Fortunately, we can provide those to ourselves. Now, before I do that, I just want to note that I will be thinking about the derivative. I'm sorry, not the derivative, the function f as 1 minus x to the negative first power. That's what I'll be thinking about when I'm taking the derivatives here. Okay, so when I do that, the first derivative is going to be negative 1 times the quantity of 1 minus x to the negative second power. Utilizing the chain rule means I have a 0 minus 1, or if I simplify, the negative 1 and the negative 1 multiply to make positive 1. So I have 1 over 1 minus x quantity squared, or as I've written it here, 1 minus x to the negative second power. Okay, when I evaluate it at 0, I have 1 minus 0 to the negative second, which is positive 1. So the second derivative is going to be the derivative of this. I remember, of course, to use the chain rule. So it's going to be negative 2 times the quantity of 1 minus x to the negative third. Derivative of 1 minus x is negative 1. Evaluated at 0, I have a negative 2 times 1 to the negative third power times negative 1, which ends up being positive 2. And I'd repeat this process until I'd satisfied what I needed to satisfy. So if I needed 10 terms, 10 terms, 5 terms, 5 terms, however many terms. We're going to do one more term here. We're not going to go for tons of terms. Okay. So we continue. Take the derivative here. It's negative 1 times negative 2 is positive 2. So it's positive 2 times negative 3 times the quantity of 1 minus x to the negative fourth times negative 1 from the chain rule. When I let x equal 0, I get 6. So I've got f of 1 is 1. F prime of 1 is 1, so it's 1 plus 1x. F double prime of 0, that's 2. 2 divided by 2 factorial. F triple prime of 0, 6. 6 divided by 3 factorial. Or, when I put them together, I have this. Note that 2 is 2 factorial, 6 is 3 factorial, 24 is 4 factorial, and 120 is 5 factorial. Or refer back to the previous thing, what keeps happening with the exponents? Well, when I take the fourth derivative, I'm going to have a 1 times 2 times 3 times 4 with a negative sign, of course. And then when I take the next derivative, I'll have a 1 times 2 times 3 times 4 times 5 factorial. Next derivative would be 1 times 2 times 3 times 4 times 5 times 6 to the power of 7. And what I'd like you to do while you're writing this down is write in what you think a formula for the nth term would be. Quick pause. Okay, we're back with our guess. Did you have negative 1 to the nth power times x to the power of n? I hope so. I suppose you could have had an n factorial divided by n factorial in there. That would have been fine. A little bit extraneous, but fine. or as the kids say, extra. Okay. So how about the interval of convergence? How are we going to do that? Well, the interval of convergence is, of course, done with the ratio test. So I do the ratio of the n plus 1th term to the nth term. Negative 1 to the n plus 1, x to the n plus 1, divided by negative 1 to the n, x to the n. I simplify. The negative 1 to the n's, those make 1. So I have negative 1 to the first power in the numerator. The x to the nth powers, those also make 1. So I have x to the first power in the numerator, or I have the absolute value of x. Nifty. As I'm interested in convergence and I'm employing the ratio test, what must be true is the absolute value of x must be less than 1. The absolute value of x is not less than 1. We don't have an interval of convergence. So we have to determine what are the feasible x values. Solving the inequality means we have a negative x is less than 1 and a positive x is less than 1. Negative x is less than 1 requires a little bit of solving, multiplying both sides by negative 1. So the direction of the inequality changes. So right now, we are considering for convergence the value of x between negative 1 and 1. And here's the part we need to make sure we remember. We don't know yet if we include the endpoints on the interval or if we exclude the endpoints on the interval. That is yet to be determined. So how do we do that? We take this value of x, negative 1, and that value of x, we substitute into the series. We take this value of 1, and we substitute that into the series. So what we have in the first case is negative 1 to the n, x becomes negative 1 to the n, which simplifies into positive 1 to the nth power. When x equals 1, we have negative 1 to the n times 1 to the n, which simplifies into negative 1 to the nth power. So the question is, for each of those series, does each series converge or diverge? And you can't be doing one of the, well, it kind of looks like it converges, or maybe it diverges. You can't do that. You have to think about a series test. This is one of those reasons why we spent so much time learning all those series tests. So if you have 1 to the nth power, does that converge or diverge? Which test would you use? I can think of a couple that could work. Here's what I chose to use. I chose to use the geometric series test. First term is 1. R is also 1. The absolute value of 1 equals 1. That means that this is a divergent geometric series. How about negative 1 to the n? Again, you can't be dithering around here. You can't be like, well, I think it's going to divert. No. You need to name a specific test. I chose again to use the geometric series test. In this case, r is negative 1. The absolute value of negative 1 is still equal to 1. So the interval of convergence starts at negative 1, ends at positive 1, and includes neither negative 1 nor positive 1. This is centered at 0. Check out the x's, right? All these x's, plain x, not x minus 1, so I know it's centered at 0. And the radius of convergence is 1, because if you go from 0, 1 unit to the right, you get to 1. If you go from 0, 1 unit to the left, you get to negative 1. Interval of convergence. Let me pause here for questions. We are going to continue by doing the exact same problem we just did. So everything except the interval of convergence. So all this stuff right here, differently. And this is what it's based off of. So f of x equals 1 divided by 1 plus negative x reminds me of 1 divided by 1 plus positive x. Those look very similar, don't they? Mm-hmm. They sure do. They look very, very similar, right? Okay. What about this thing on the right? Do you recognize this thing on the right? You're supposed to. This is on the list of the 4 Maclaurin series you're supposed to be memorizing. So 1 divided by 1 plus x, that was one of the formulas, one of the functions that we want to know the Maclaurin series for. So the terms, the first 4 non-zero terms, 1 minus x plus x squared minus x cubed. Formula for the nth term is negative 1 to the nth power times x to the nth power. I'm going to use this observation right here to do all of that work we just did. So remember all those derivatives we did, all those calculations we did? I'm going to do all of that by using this observation that these are very similar. How am I going to do that? Well, by saying this is the case. Check that out. So what I did was I said, hey, this right here and this are the same, but for the negative x is in the x spot. So I looked at this formula here and I said, I would like to have a negative x in the x spot. And if we use this formula, we're going to get all of the exact same terms we came up with up here. You can test it. 1 times 1 is 1. Negative 1 times negative x is positive x. When n is 2, negative 1 to the second, negative x to the second is plus x squared. When n is 3, negative 1 to the third, negative x to the third is plus x to the third. Works the same way, doesn't it? Much more time efficient, isn't it? That, my friends, that is the math we want to study today and tomorrow. But for today, we're going to look at this function. And we're going to write the Maclaurin series in summation notation for this new function f. This new function f is the sine of x squared. I'm not going to repeat everything we said about Maclaurin series in terms of writing it. Just going to remind you that a Maclaurin series is a Taylor series with 0 for the center. So it looks like this. So that means I need f of 0, f prime of 0, f double prime of 0, f triple prime of 0, fourth derivative of f at 0, fifth derivative of f at 0, sixth derivative of f at 0. Okay, we can do all that, right? Of course we can. We can evaluate this at 0. That's not too bad. You get sine of 0 squared. 0 squared is 0. Sine of 0 is 0. But when you start doing the derivatives, you pretty quickly get into a hot mess because when you take the derivative of sine of x squared, you need the chain rule. The derivative of sine is cosine. So we have cosine of x squared times the derivative of the inside function. Derivative of x squared is 2x. Think about what happens when you go to take the next derivative, the second derivative. Not only do you need the chain rule, You also need the product rule. So when you go to take the derivative of cosine of x squared, you get negative sine of x squared, but you have to multiply by 2x. So it's negative sine of x squared times 2x times the 2x plus, this time I'm going to take the derivative of 2x. So I have cosine of x squared times 2. Again, manageable, doable. We know how the product rule works for derivatives. We know how the chain rule works for derivatives. Not a big deal. What I want you to think about is what happens for the next derivative and the derivative after that. When you go to do the third derivative, you're going to need the chain rule again. You're going to need the product rule here. You're going to need to do the derivative of negative sine of x squared times 4x squared. So you're going to need the chain rule and product rule to do that. You're also going to need the chain rule and the product rule here. And then when you go to take the fourth derivative, you're going to have to do the chain rule and the product rule again for multiple terms. It's going to take forever. Forever. We would like to avoid forever. So how could we do this more elegantly? How could we do this more efficiently? That's what we're interested in. And the answer to that requires you to have this information. What is the Maclaurin series for sine of x? The Maclaurin series that you have been memorizing. Good place to pause. Okay. And you should also know the formula for the nth term. Formula for the nth term, does it look like that? Is that right? Negative 1 to the n, x to the 2n plus 1 power, 2n plus 1 factorial. Is that right? I'm going to leave it there. If it's not right, it's not right. It's up to you. That one's up to you. So, why did I ask you to think about the Maclaurin series for sine of x? Well, there's two reasons that might help you know what's going on here. The first reason is we're talking about the Maclaurin series. So it makes sense, right? Maclaurin series, Maclaurin series. The other thing that might make sense to you is if I observe this to you. Sine of x squared is sine, the sine function, with x squared in the argument instead of x. So there is absolutely no reason why, if I do the same thing on both sides, namely replace x with x squared, so substitute x with x squared, I can't do that. That's algebraically sound. That's perfectly fine to do, algebraically speaking. If you do the same thing on both sides, that's okay. So I evaluated x squared. So instead of x, I have x squared to the first power. Instead of x to the third divided by 3 factorial, I have x squared to the third power divided by 3 factorial. Plus x squared to the fifth power divided by 5 factorial. Minus x squared to the seventh power divided by 7 factorial. Another good place to pause. I also like noticing how the exponents, and you may not have done it this way, and that's fine. I just like sharing some additional math with you. Go from 2 to 6 to 10 to 14, right? Because 2 times 1 is 2, 2 times 3 is 6, 2 times 5 is 10, 2 times 7 is 14. And that has a pattern of adding 4, which is arithmetic. Right? If you add 4, you're arithmetic. And we have a formula for writing arithmetic. First term plus the common difference times quantity of n minus 1. So we could also use x to the power of 4n minus 2. Now we do need to be a little bit careful here because 4n minus 2, if n equals 0, doesn't work out. We get a negative 2 for the first term for n equals 0. But for n equals 1, works out just fine. Okay. Timing's working out just a little bit differently here for you all. So we're going to do another example instead of what I'd originally planned. We'll do what I originally planned tomorrow. So here's what I'd like you to do. I want the Maclaurin series for the cosine of the square root of x and the interval of convergence. Go ahead and work on that. I hope you started off with the Maclaurin series for cosine. Here's the first four terms. Here's the nth term in summation notation. I can evaluate cosine at the square root of x. When I do that, I have the square root squared, so first power, square root to the fourth, which is second power, square root to the sixth, third power, etc., etc. So then I sat down and I figured out what's my formula going to be. So I need x to the 0, 1, 2, 3 power and the 2, 4, 6 factorial. So I settled on x to the nth and 2n factorial. When we do the ratio test for the interval of convergence, we have the n plus 1th term divided by the nth term. I multiply. 2n plus 2 factorial and 2n factorial, simplify into 2n plus 2 times 2n plus 1 in the denominator. Negative 1 to the n plus 1, negative 1 to the n, simplify into negative 1 to the first power in the numerator. X to the n plus 1 and x to the n, simplify into x to the first power. As n approaches infinity, this approaches 0 because the denominator dominates the numerator. Since 0 is always less than 1, then for any value of x, this converges. So the radius of convergence is infinite, and the interval is all real numbers x.